The roar of water crashing down, powerful enough to be heard from miles away. The mighty Itaipu Dam thunders with an impressive capacity, generating up to 27,000 megawatts of electricity, more than enough to power the needs of millions. Within this monumental structure lies a hidden marvel of engineering, the Francis turbine. A series of these massive turbines, each weighing several hundred tons, are positioned not just haphazardly but at an exact orientation, straight down into the earth. Such a peculiar arrangement demands exploration. Why on earth would engineers decide to install turbines in this vertical configuration? To understand this decision, we must first explore the nature of the forces at play. Imagine a heavyweight boxer, he carries a significant mass. Now envision that same boxer punching downward with incredible force. If you were to place a scale beneath him, the scale would register the punch not just due to gravity but the sheer momentum he generates. That boxer represents the pressure harnessed by these turbines, utilizing hydrostatic head rather than simply relying on gravitational forces. The Itaipu Dam receives its power not simply from the weight of the water but from the pressure of water acting upon these turbines due to its depth. Upstream, the water level might be a staggering 25 meters high. This translates to massive pressure, capable of pushing tons of water down through the turbine shafts. This is where we encounter a significant aspect of the design, the thrust bearing. Each Francis turbine at Itaipu is subjected to pressure loads that can exceed 3,000 tons. It seems almost incomprehensible, how can a mechanism, seemingly reliant on mere gravity, bear such immense weight and pressure? Nonetheless, turbine designs are not just about brute force but require calculated precision. The vertical orientation of Francis turbines means that the turbine runner, where the water does its critical work, sits below the generator. The generator, positioned above, transforms mechanical energy into electrical energy. This results in a crucial advantage. By utilizing hydrostatic head pressure, the bearings can be optimized for operational loads while dramatically reducing the complexity of the structural design. Picture the turbine as a giant screw pushing through a thick piece of wood. To efficiently create a hole, it utilizes rotational force to drive downwards. The deeper the screw penetrates, the harder it works, yet it remains remarkably efficient. Unlike a traditional horizontal turbine system, whose bearings would be subjected to constant wear and tear due to the weight of the machinery above them, vertical turbines utilize the weight of water as a natural advantage against downward forces. This major alteration in design reduces failure rates and enhances the longevity of the turbine itself. Yet, let's consider the hydrostatic head pressure in greater detail. Engineers estimate that for every meter of water, there's roughly 100,000 pascals of pressure. Multiply that by the 25 meters in depth, and you find that the operational pressure can reach upwards of 2.5 million pascals. This immense force forces the water through the turbines, but how does it all translate into the electrical energy that powers homes and industries? The answer lies in the clever design of the turbine runner. Featuring adjustable blades, the turbine can optimize its angle based on the current water flow. As water spirals through the blades, its velocity transforms kinetic energy into rotational energy. This motion ultimately drives the generator above, which then produces electricity. However, you might assume that a turbine should operate best at maximum speed. In fact, it is most efficient when operating at approximately 80% of its maximum capacity. This maximizes the conversion of kinetic energy into electrical energy while preserving mechanical components from excessive wear and heat. At this point, let's take a moment to engage with a thought. If you were to choose between standing next to a helicopter, a high-speed train, or a colossal dam with its turbines humming beneath, which machine would you least want to be near? Consider the sheer power generated by each system. The dam may seem the most benign, with its steady, slow flow of water, but its underlying mechanics are anything but. But let's address a common misconception. Many people tend to believe that horizontal turbines, aligned with gravity, should naturally produce greater efficiency, considering gravity's direct influence. In truth, this is far from the optimal choice. Because Francis turbines are designed to utilize hydrostatic pressure, they can better manage thrust loads, meaning that this design can preserve the integrity of the system even under immense stress. Their vertical installation not only aids in supporting the machinery itself but naturally collects and directs water through a more controlled environment. In essence, the engineers at Itaipu and other facilities like it are harnessing the natural properties of water in novel ways. The relationship between the kinetic and potential energy, these turbines signify a leap in the evolution of hydropower mechanics, reflecting deep understanding and innovative application. At a typical installation, a single Francis turbine can harness 500 megawatts of energy, illustrating the capacity for enormous production. With 14 turbine units operating efficiently, Itaipu has demonstrated the sheer power of sound engineering coupled with nature's relentless momentum. When water moves through these turbines, it doesn't just generate energy, it reflects the wonders of human ingenuity and our ability to align our creations with the elements of nature. To conclude, each turbine at Itaipu can be viewed as an exquisite balance of pressure and form, maximizing energy while minimizing waste. Their design, a testament to the brilliance behind hydroelectric power, teaches us an essential principle of engineering. Sometimes the most efficient solutions lie in embracing the unexpected and working in harmony with the forces of nature, rather than against them. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you. As we delve further into the mechanics of Francis turbines, it's essential to understand the intricate relationship between water flow and turbine efficiency. The design of these turbines is meticulously optimized for the conditions in which they operate. Each component serves a specific purpose, enhancing the overall functionality while minimizing energy loss through friction or turbulence. The shape of the turbine blades is paramount. Rather than being entirely flat, they are contoured to create an environment where water flows smoothly over the surface, enhancing both efficiency and reducing cavitation, an issue where low-pressure bubbles form and can damage the turbine. Each blade is angled for maximum performance against varying flow rates. Engineers utilize computational fluid dynamic simulations to design and refine the blade shapes, adjusting their profiles to achieve the best hydraulic performance. This allows the turbine to operate efficiently under a range of conditions, adapting to changes in water availability or flow rate caused by seasonal rainfall or snowmelt. In systems like Itaipu, where water availability can fluctuate, the capability of the turbines to adjust their performance dynamically is crucial. The strategic design allows for adjustments in real time. Engineers can modify the blade angles while the turbine is operational to optimize output for changing water conditions. This adaptability is a significant part of why Francis turbines have become a standard in hydroelectric technology worldwide. We should also consider the implications of scale in the context of hydroelectric generation. Itaipu stands as a remarkable human achievement, but it is part of a broader narrative within hydroelectricity that stretches back centuries. Before modern turbines, early water mills harnessed kinetic energy with rudimentary designs made from wood and stone. These basic principles have evolved tremendously. For example, the first turbine invented by Benoit Fourniron in the early 19th century laid the foundation for modern turbine design. His innovations facilitated improved efficiency by maximizing water flow impact on the turbine's runner. Let's return to Itaipu for a moment and consider its size. Not only does it generate a staggering amount of electricity, it also operates under immense structural constraints. The concrete dam stretches about 7,090 meters long and rises 153 meters above the Parana River. This ambivalent mass combines gravity and hydrostatic pressure in a perfect embrace. Engineers have carefully calculated how each component, the dam wall, the turbines, and the associated generators, interacts to support massive environmental pressures. Under enormous external stresses, such as water volume and back pressure, the thrust bearing becomes crucial in the vertical turbine arrangement. The thrust bearing supports not just the weight of the turbine itself but also the dynamic loading generated by water entering the turbine. This load can be overwhelming, reaching forces upwards of 3,000 tons during peak operational times. Each bearing is designed to withstand these loads, ensuring the smooth operation of the turbine, avoiding mechanical misalignment or breakdowns. Take, for instance, the recent innovations in thrust-bearing materials. Many companies are now employing advanced composite materials, which can further withstand significant hydrodynamic and thermal stresses. Innovations in material science help engineers extend the lifespan and efficiency of these components, thus optimizing the system overall. As the water turns through the turbine, a fundamental transition occurs. Kinetic energy is transformed into rotational energy, and then further into electrical energy by the generator located above the turbine. This conversion is not straightforward, there are many subtle dynamics at play. The generator itself consists of a rotor spinning within a magnetic field established by stator coils. When water spins the turbine, it turns the rotor. As it does, magnetic induction generates electricity. Imagine the hundreds of tons of water cascading down from the reservoir. That immense force is what triggers this entire operation. Notably, the efficiency of this water-to-electricity conversion is affected by the size of the generator and, consequently, the turbine. For Itaipu, the combination creates an impressive efficiency rating typically in the magnitude of 90% across its operational range. This high efficacy ensures that as much energy as feasible is harnessed rather than lost as excess heat or friction. But how does Itaipu compare on a global scale? It is one of the largest hydroelectric plants alongside the Three Gorges Dam in China. Three Gorges utilizes a different kind of turbine, showcasing how diverse design choices can impact performance based on geographic and hydrological factors. While Three Gorges employs bulb turbines optimized for river flow conditions, Itaipu showcases the effectiveness of France's turbines under variations in height and head pressure. The comparison offers a relatively straightforward exam of how engineering preferences align with environmental conditions. In addition to its power generation, Itaipu also serves other purposes. It is an essential reservoir for flood control and water storage during dry seasons, thus enhancing agricultural performance in surrounding regions, demonstrating that the engineering behind these turbines has broader societal implications. Now, let's consider the impact of these systems on local ecosystems. Hydro plants like Itaipu instantly alter the natural flow of rivers and create reservoirs, leading to changes that can affect fish populations and overall biodiversity. Understanding these impacts is critical. Engineers and ecologists collaborate to mitigate adverse effects, enabling fish passages and utilizing design strategies that preserve local fauna while still providing the necessary energy output. Moreover, this relationship extends beyond just mitigating backflows and searching for ecological solutions. Turbines can contribute positively to the local environment. As large bodies of water accumulate behind dams, they create habitats for diverse wildlife, transforming previously untamed regions into thriving ecosystems. The use of responsible engineering practices emphasizes the balance between nature and human habitation. Let's reflect again on the operational safety and maintenance practices surrounding these turbines. Regular inspections, preventive maintenance, and rigorous safety procedures ensure their long-term functionality. They involve everything from scrutinizing the integrity of thrust bearings to monitoring hydrostatic pressure specifics. Engineers rely on sophisticated monitoring systems that capture real-time data, aiding in everything from performance assessment to predictive maintenance analytics. Sophisticated sensors can notify operators before an issue escalates, making failure prevention a proactive endeavor. Listening to the sounds of the turbines at Itaipu, one finds a mechanically symphonic ecology where human design and nature entwined in a rhythmic dance. Amongst the hum of machinery, the rush of water echoes as a reminder of the power harnessed through carefully orchestrated designs. Ultimately, the interplay between force and engineering exemplifies the principles at the heart of hydropower. The very configuration, these vertically mounted Francis turbines, embodies the marriage between ingenuity and nature's raw potential. With careful design, choosing to exploit hydrostatic pressure rather than straightforward gravitational pull has resulted in machines that can withstand immense stress while maintaining efficiency. In closing, we forge connections with the engineering marvels around us, understanding just how simple principles can create structural feats beneath our feet, often unnoticed but impressively effective. The beauty lies in human creativity that transforms the chaos of nature into a profound utility, capturing energy while respecting the delicate balance of ecosystems. The bigger the machine,